Welcome to For Science Salah Lotfy channel. Today we introduce a fascinating research breakthrough, a new modeling and simulation technique called the Conceived Predictive Diagonal, or CPD. What makes this technique so remarkable? It shows us that with only 4 carefully chosen data points, we can model complex chemical and physical systems with high accuracy, something that usually requires dozens of experiments. This approach, based on nonlinear regression and MATLAB simulation, has already been successfully applied in several fields. Examples include the catalytic oxidation of arsenic, the conversion of glycerol into valuable chemicals, the capture of carbon dioxide using advanced ceramic materials, and even the removal of uranium from industrial solutions. The scientific value lies in simplifying complex systems into accurate and reliable models. The technical value comes from faster simulations and easier optimization. The economic value is clear: fewer experiments, lower costs, and faster development cycles. And the practical applications are wide-ranging, from nuclear waste treatment and environmental protection to chemical industry processes, water purification, and even advanced energy systems. In short, CPD is not just a new tool for researchers, but a potential game-changer for multiple industries. Stay with us as we explore this innovative technique in detail, right here on For Science Salah Lotfy channel.
Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today, we will introduce an innovative research work published in the Journal of Basic and Environmental Sciences, Volume 7, 2020, pages 213 to 220. The research is titled, A Novel Technique, Conceived Predictive Diagonal, CPD, Graphical Nonlinear Regression Modeling and Simulation. It was authored by Professor Dr. Ebrahim Abd El-Gawad from the Nuclear Materials Authority, Maadi, Cairo, Egypt. His academic profile is also registered under OR-CID 000018276661. Now, what is this research about? The study introduces a brand new technique called the Conceived Predictive Diagonal, or CPD. This approach is designed to simplify complex experiments and save both time and resources. Instead of relying on large experimental datasets, CPD shows that just 4 diagonal points from a carefully designed matrix can be enough to model a system with high accuracy. Using nonlinear regression and MATLAB simulation, this method was tested on several scientific and industrial applications: catalytic oxidation of arsenic, conversion of glycerol into valuable chemicals, carbon dioxide capture using lithium orthosilicate, and uranium removal from nitrate solutions using ion exchange resins. The results proved to be remarkably close to the experimental data, demonstrating the power and reliability of this new approach. The significance of this work can be summarized in 4 dimensions: scientific value, simplifying complicated systems while maintaining high precision; technical value, enabling faster simulations and easier optimization; economic value, reducing costs by cutting down the number of required experiments; practical value, wide applications in nuclear engineering, environmental protection, chemical industries, water treatment, and advanced energy systems. In short, the research by Professor Dr. Ebrahim Abd El-Gawad presents CPD as a powerful modeling technique that could transform how experiments and simulations are carried out across multiple disciplines. Stay tuned as we explore the details of this fascinating work, right here on For Science Salah Lotfy channel. Welcome back to For Science Salah Lotfy channel. We introduced the groundbreaking Conceived Predictive Diagonal technique, or CPD, developed by Professor Dr. Ebrahim Abd El-Gawad from the Nuclear Materials Authority in Cairo, Egypt. We saw how this new approach revolutionizes experimental modeling by relying on just 4 diagonal points of data to simulate complex reactions with high accuracy. Today we will dive deeper into how this technique was verified and how it performed across several practical examples. Segment 1. Verifying the technique. To prove that CPD can actually work as a modulus operandi, meaning a reliable operating method, Professor Dr. Abd El-Gawad established a clear, structured verification procedure. Here's how it works. 1. Gather practical data. This data could come from experiments already performed, whether based on traditional or new approaches. 2. Add an initial reference point, called x0, y0, z0, to each vector in the dataset. This ensures that the simulation starts with a meaningful baseline. 3. Simulate the suggested models using MATLAB's powerful tool called CFTool, short for Curve Fitting Tool. This allows the researcher to generate graphical models of how 2 variables, such as time and temperature, affect a third, the response. In some cases, another MATLAB tool called EasyFit can also be used for quick curve generation. 4. Compare the simulated results to real published experimental values using statistical indicators such as the correlation coefficient, ER, the coefficient of determination, R2, and the adjusted R2. These metrics tell us how close the simulated model is to real laboratory data. 5. Finally, the data cursor tool in MATLAB is used to make fine comparisons, allowing the user to hover over points in the graph and check their numerical accuracy directly. This systematic verification ensures that CPD isn't just a theoretical idea, it's a practical, testable, and repeatable modeling technique. Segment 2. Numerical example. 1. Arsenic oxidation. To demonstrate the method, Professor Dr. Abd El-Gawad first applied CPD to a study by J. Zhao and co-authors, titled Rapid and Efficient Catalytic Oxidation of As3, with oxygen over a platinum catalyst at increased temperature. In that study, researchers examined how arsenic-3, a toxic form of arsenic, oxidizes into arsenic V under different temperatures and times using a platinum catalyst. The data table, or matrix, included concentration values for ASV at various time and temperature combinations. However, the matrix was not square, and the CPD technique requires a square matrix to extract the diagonal. So, a new square matrix, called CASM, was created using 4 key time values, 10, 30, 60, and 120 minutes, and 4 temperature points, 293, 313, 333, and 353 Kelvin. By taking the diagonal values of this matrix, Professor Dr. Abd El-Gawad obtained just 4 data points, 1, 4, 11, and 19 ppm. Using MATLAB's CFTool, these points were then used to construct 2 graphical models, one based on transition theory, and the other based on the Arrhenius equation, which relates reaction rates to temperature and activation energy. The results were impressive. The activation energy and pre-exponential factor, K0, calculated from the CPD model were 31.6 kJ/mol and 1.05 x 103 respectively, almost identical to the original experimental values of 31.1 kJ/mol and 1.05 x 103 mol the 05 L05. Even more striking is that these highly accurate results were obtained from only 4 diagonal points, instead of dozens of full experimental data points. The statistical accuracy was also exceptional. R2, 0.99982, adjusted R2, 0.9982, RMSE, root mean square error, 0.3385. Such high correlation confirms that CPD successfully reproduces the system's behavior using minimal data, validating the core hypothesis behind the technique. Segment 3. Numerical example. 2. Glycerol conversion. Next, CPD was applied to a completely different reaction system, one involving glycerol, a common byproduct of biodiesel production. In this case, the reference study came from Sarawali Thanasilp and colleagues titled One-Pot Oxide Hydration of Glycerol to Value-Added Compounds over Metal-Doped Psi-W HZSM5 Catalysts. The experiment investigated how temperature and time affected the conversion of glycerol into valuable chemicals. The temperature range was between 333 K and 363 K, and the reaction time ranged from 0 to 80 minutes. Once again, the original data matrix was not square, so Professor Dr. Abd El-Gawad constructed two square matrices, XS1 and XS2, representing two sets of temperature and time combinations. Example 2.a. For XS1, the time points were 10, 20, 30, and 40 minutes, and the temperature points were 333, 343, 353, and 363 Kelvin. From this matrix, four diagonal conversion values were selected. After applying the Arrhenius model, the activation energy, dE, was calculated to be 26.63 kJ/mole, exactly matching the reported experimental value. The statistical fitting showed R2, Da, 0.9968, again, a near-perfect match. Example 2.b. For XS2, slightly different time intervals were used, 10, 20, 40, and 80 minutes, to test the robustness of the technique. The results were almost identical, confirming the reproducibility of CPD under different data sampling conditions. The MATLAB-generated 3D plots showed clear, smooth surfaces representing glycerol conversion as a function of time and temperature, all derived from just four diagonal points. This second example further demonstrated that CPD could accurately simulate complex chemical kinetics while reducing the need for extensive experimentation. In both examples, the CPD-based simulations were compared directly with experimental studies that used traditional kinetic modeling, yet CPD achieved the same or better accuracy with less than 10% of the data. The method also provides a visual, intuitive understanding of reaction kinetics using MATLAB's interactive 3D plots. With tools like CFTool and Data Cursor, researchers can inspect the model, adjust variables, and instantly see how the system responds. From a scientific perspective, CPD merges nonlinear regression, thermodynamics, and kinetic modeling into a unified framework. From a technical perspective, it makes MATLAB not just a computational tool, but an experimental partner. Segment 5. Broader implications. The success of these examples opens doors to vast applications, not only in chemistry, but across multiple disciplines. Environmental engineering, modeling pollutant degradation with minimal testing. Nuclear science, predicting uranium or rare earth extraction efficiency. Catalysis, research, optimizing temperature and pressure conditions faster. Industrial processing, reducing time and cost in large-scale chemical design. By transforming how we interpret limited data, CPD offers a future where experiments are smarter, faster, and more efficient, without compromising accuracy. To summarize, Professor Dr. Ebrahim Abd El-Gawad's Conceived Predictive Diagonal, CPD technique, proves that science can achieve precision not by doing more, but by doing smarter. Through innovative mathematical modeling and the power of modern computational tools, this method redefines the balance between experimental effort and scientific insight. We'll continue with further applications of CPD, including its role in carbon dioxide capture and uranium ion exchange systems. Stay tuned, and don't forget to subscribe for more scientific explorations here on For Science Salah Lotfy channel. We continue exploring the research of Professor Dr. Ebrahim Abd El-Gawad from the Nuclear Materials Authority in Cairo, Egypt, who developed a revolutionary modeling method called the Conceived Predictive Diagonal, or CPD. We discussed how CPD simplifies complex kinetic modeling by relying on only a few diagonal data points instead of entire experimental datasets. Now, we'll look at the third example in this study, one that deals with one of today's most critical global challenges: carbon dioxide capture. Segment 1, the example, CO2 capture using lithium orthosilicate. This application was based on research by Suellen M. Amorim and colleagues titled Lithium Orthosilicate for CO2 Capture with High Regeneration Capacity, Kinetic Study and Modeling of Carbonation and Decarbonation Reactions. In simple terms, the study examined how lithium orthosilicate, Li4SiO4, captures and releases carbon dioxide under controlled thermal conditions. This process involves two key reactions: carbonation, when CO2 is absorbed, and decarbonation, when CO2 is released during regeneration. Professor Dr. Abd El-Gawad focused on the isothermal decarbonation phase, where Li4SiO4 releases captured CO2 at constant temperatures ranging from 550 to 700 Kelvin. The experiment's time intervals were 15, 30, 60, and 65 minutes, and the results were represented as conversion ratios, showing how much of the material reacted over time. From this data, a square matrix was created and its diagonal elements were extracted. Again, just 4 data points representing the system's core behavior. These diagonal values were then analyzed using MATLAB's curve-fitting tools, applying what is known as a shifted pseudo-order kinetic model. This model recognizes that reactions don't always follow perfect zero or first-order kinetics. Instead, they can shift between these states depending on temperature and time. By representing the diagonal both in 2D and 3D, Professor Dr. Abd El-Gawad determined the system's maximum conversion, Xmax, about 0.998, meaning the material was almost fully regenerated. The apparent activation energy, DE, for this decarbonation process was found to be 56.62 kilocalories per mole, which matched the original experimental report by Ebrahim and her team. This level of agreement, with such minimal data, demonstrates the true predictive power of the CPD approach. The results of the CPD simulation were extraordinarily precise. The sum of squared errors, SSE, was as low as 2.1 x 10 to the 5, while the coefficient of determination, R2, reached nearly 1,000, indicating an almost perfect correlation between simulated and experimental data. The root mean square error, RMSE, was approximately 0.003, a level of precision rarely achieved in kinetic modeling. These statistics prove that the shifted pseudo-order model, powered by CPD and nonlinear regression, can reproduce complex thermal reaction kinetics with outstanding accuracy, all from just a handful of carefully selected data points. This example is particularly important because it shows that the CPD technique is not limited to simple chemical reactions. It can also handle multi-step processes like CO2 absorption and release. That opens doors for advanced modeling in energy and environmental research, especially in designing and optimizing carbon capture materials and systems. Beyond CO2 capture, the CPD method's efficiency could transform other fields, such as nuclear material processing, adsorption studies, and industrial catalysis, where time, cost, and precision are critical. In conclusion, through 4 different examples, from arsenic oxidation, to glycerol conversion, to carbon dioxide capture, and uranium ion removal, Professor Dr. Ebrahim Abd El-Gawad proved that the Conceived Predictive Diagonal, CPD technique, can model complex systems accurately, quickly, and with far fewer experiments. By combining nonlinear regression, MATLAB simulation, and thermodynamic principles, this method allows researchers to visualize and understand chemical and physical systems in a much simpler way. Professor Dr. Abd El-Gawad dedicated this work to the memory of his late mentors, Dr. Abdul Karim Abul Hassan, Dr. Nabil El-Hazek, Dr. Ahmed Kazbak, and Dr. Muhammad Abdel Hakam Maadi, and extended his gratitude to the Nuclear Materials Authority, the Department of Chemical Engineering at Alexandria University, and MathWorks R, the creators of MATLAB. This research stands as a powerful example of how creativity and computational science can come together to make experimental modeling more efficient, accessible, and accurate. Stay tuned for more scientific explorations and discoveries, right here on For Science Salah Lotfy channel. Dear viewers, this is Professor Dr. Salah Lotfy from the Egyptian Atomic Energy Authority. In today's closing segment, I would like to take a moment to express my sincere appreciation to Professor Dr. Ebrahim Abd El-Gawad from the Nuclear Materials Authority, Maadi, Cairo, for his exceptional effort and scientific dedication in preparing and publishing this remarkable research work. Through his study, a novel technique, Conceived Predictive Diagonal, CPD, graphical nonlinear regression modeling and simulation, Professor Dr. Abd El-Gawad introduced an innovative and intelligent approach to scientific modeling, one that simplifies complex experimental systems and reduces the number of required tests while maintaining an impressive level of accuracy. His creative use of nonlinear regression and MATLAB simulation has opened new pathways in chemical kinetics, thermodynamics, and environmental applications, contributing significantly to both the Egyptian and international scientific communities. As a fellow researcher, and as someone deeply involved in scientific development at the Egyptian Atomic Energy Authority, I take great pride in highlighting and celebrating the achievements of Egyptian scientists who continue to push the boundaries of innovation. Their efforts, like this one, serve as an inspiration to young researchers and demonstrate that with creativity and perseverance, great science can be achieved anywhere. I would also like to extend my heartfelt thanks to all of you, our loyal followers on For Science Salah Lotfy channel. Your continued engagement, encouragement, and curiosity are what keep this scientific journey alive. I invite you now to share your thoughts about this research in the comment section below. What do you think about the conceived predictive diagonal technique and its potential impact on scientific modeling and data simulation? Your feedback is valuable and always appreciated. Thank you for watching, for supporting science, and for being part of this growing community that believes in knowledge, innovation, and the spirit of discovery. Stay connected for more insightful discussions, only on For Science Salah Lotfy channel.